di questo colloquio, grazie per essere intervenuti. E abbiamo un ospite importante che è la professoressa Beatrice Fraboni dalla Università di Bologna, tra parentesi l'Università di Bologna è la più antica d'Italia e viene l'Università di Catania la più antica del sud, cioè abbiamo il sud dove si sta. Vabbè, andiamo a Napoli. Federico II. Federico II. Non so da Federico II se in qualche modo, non credo sì. La professoressa Fraboni ci parlerà, diciamo, il titolo lo vedete, diciamo che è una sintesi della sua importante carriera. Lei è direttrice del Collegio Superiore, presidente dell'Istituto di Studi Superiore Bologna, e quindi oltre a importanti incarichi, oltre a questa alla importante linea di ricerca, e dulcis in fundo abbiamo per la professoressa Fabroni che la dirà il concludere.
Dare un tocco personale, perché conosciamo Beatrice, noi realizziamo adesso da circa 30 anni, quindi abbiamo cominciato la collaborazione quando ancora lei lavorava sul silicio, perché la sua attività è essenzialmente sui semiconduttori organici, inorganici prima, organici dopo. Comunque abbiamo cominciato a collaborare quando si trattava di difetti in silicio, impiantazione ionica, lei faceva le analisi, e poi questa collaborazione essendo andata avanti, lei ha sempre approfondito con grande successo quello che è stata le proprietà di trasporto elettriche e elettroniche ed optoelettroniche dei semiconduttori inorganici e organici. E poi però credo che dal mio punto di vista, che sono scarsa da questo punto di vista, c'è più grande successo nel trasferimento tecnologico. Lei è stata attivissima, ha fondato uno spin-off e titolare di ben 17 brevetti, tratta con le ditte, quindi di fatto è riuscita a fare una sintesi, una grande sintesi tra l'attività scientifica e l'attività di trasferimento tecnologico, che è una cosa non comune, perché tutti noi che facciamo i fisici, cioè, generalmente tendiamo a fare la fisica e l'altra parte la glissiamo, per lei veramente la porta davanti. Quindi grazie Beatrice di essere venuta.
Grazie a voi. Bene. Allora, io provo a parlare da qua, se non mi sentite mi metto...
Non c'era.
C'era, però abbiamo detto che forse se sto in piedi... perché dietro mi sento un po' claustrofizzata. Secondo... lo mettiamo? Allora va bene, lo mettiamo. Va bene. E quindi volete che faccia la presentazione in italiano o in inglese? Ci sono... In inglese, ok.
Questo lo mette al bavero e questo lo mette in tasca da qualche parte. E poi...
Ok, mi sentite? No, è chiuso. Ecco. Ok. Se mi sentite... Un pochino, intanto parlo così magari aggiustiamo il volume nel frattempo. Okay, so first of all, thank you very much for inviting me, and it's really a pleasure to be here collaborating with these colleagues and meeting again these colleagues I've been working with for many, many years. And thanks to the rector for being here today. It's really a great honor, and I'm really happy to say that we've really worked together and known each other for many years. So today, what I'm going to discuss and to show you is actually not really a summary of my work, but the recent research that I'm carrying out that goes in the direction that Professor Grimaldi was commenting. So I'm trying to make the best use of my fundamental research on semiconductor, transport, defective states, and their role on the transport properties of novel materials to implement applications that can be of somewhat practical use. So that's why I think I'm in between, I'm at the boundary between just physics, pure transport physics applied to semiconductors, and applied physics in terms of devices and novel tools. So I'm working presently on novel materials that can be used to develop large area ionizing radiation detectors. So the question could be why? Why? Because we still haven't got them. There are no large area ionizing radiation detectors and in general radiation detectors that can be able to detect in real time with a good performance radiation visible. But again, I'm going to work mostly today, talk about today, ionizing radiation, and many applications would benefit for such radiation detectors. What we really need are large area detectors that can be operated in real time at low power, that can be bendable, flexible, and lightweight. Think about space application where the payload is crucial. And we also need to use them to detect not only photons, but also protons, because there are many applications where particle detection is very important. Presently available technologies cannot deliver all these features at once. I'm just showing here, just as a reminder, how are presently medical diagnostic radiation detectors. So you have rigid, heavy, and detectors operated at 1,000 volts. So definitely not easy to use in many applications. And so we really need to devise new materials with all these functionalities. We can't just use easily the materials that we are normally using. We are using, other people are also using, traditional semiconductors, for example, silicon, that in its amorphous form can be used to be deposited over large areas. And in fact, the detector, the medical diagnostic sheet I was showing you before is made very often of amorphous silicon. But amorphous silicon is, however limited in the area that you can deposit it, it is stiff intrinsically and needs high temperatures and reaches eventually a bulk and heavy volume. So we need novel materials. And I've been working together, of course, with the world community on these two classes of materials, semiconductor materials, that I find really challenging: organic semiconductors and perovskites. They are very interesting because they allow to fabricate a detector, the one that you see in the image is a detector that we fabricate in our lab, which are, as you see, matrices, pixelated and very flexible, deposited on plastic. They are easy to use because they can be solution deposited. So we go for printed materials and printed electronic devices. Printing means that you don't need high temperature, you don't need complex deposition processes. You can work on non-conventional substrate, plastic, textiles, paper, whatever. Let me just go briefly. I have just two slides. One, synthesizing what are the major properties of organic semiconductors, and the other one about perovskites, because I'm not sure about how many of you are familiar with these materials. And I just want to highlight what are the major properties to understand better how they can be exploited. So organic semiconductors are based on pi-bonded molecules, typically made up of carbon, sp2 hybridized, typically linked with hydrogen, sometimes with sulfur, nitrogen, and oxygen. So definitely many different structures that you can build, very varied, but these are the atoms that constitute these materials. They can be single crystal, amorphous, polycrystalline, and thin films. So as we do for atoms, we can play around with the final form. What is interesting is that they tend to be electrically insulating unless we induce motion of charges or injection of charges with electrodes, doping, or photoexcitation. Their interesting properties is a very low dielectric constant. That means that excitons with binding energies are very, very different from the one of silicon, and they hardly dissociate at room temperature. So charge carriers are polarons, which is a charge self-localized, and its molecular distortion. So migration of these charges is not so easy. And in fact, transport of carriers is typically limited by hopping. So the mobilities cannot reach easily the mobility of silicon. What are the advantages? They are very easy to deposit because they can be deposited, as you see here, from solution or from vapor deposition, evaporation. And they allow for an extremely easy chemical tailoring. Chemists are very, very good in changing all these termination and completely changing the shape of the molecule and its final molecular packing and eventually its properties. So they're really versatile. Perovskites. Perovskites are a completely different structure. Here you see the structure of a typical perovskite, where you have an organic cation, you see it in the middle, a metal and a halide. The typical cations are, these are the long names, I'm not going to read them for you, typically are called Ma and Fa, so methylammonium and formamidinium, or cesium, that's also easy. If you use larger cations like ethylammonium, then you change the dimensionality of the structure from 3D to 2D, inducing very, very interesting different properties to this material. Again, they're very versatile, and different combinations of A, B, and X component can change the properties of this material. Their gap is typically can be varied, depending on the combination of components, between 1.3 and 2.5 electron volts. They also have a low exciton binding energy, and they have a very good lifetime, carrier lifetime and mobility. So their transport properties are more comparable to the ones of silicon. They can also be deposited by solution, and they have, what is also very interesting, a very good ambipolar behavior that can be exploited. What is interesting for our application, the one I'm going to talk about today, are the good mobility and the high atomic number that induces a very good absorption of ionizing radiation. So this is just to show you a last comment on what happens or what can be done thanks to the versatility of all these organic molecules. You can easily fabricate materials, synthesized materials and deposit them in order to have them emitting or absorbing pretty much in all the spectrum of visible light. So you can tune the performance of your material very, very easily by a chemical synthesis, and then you have this solution that you can easily deposit and thus have a completely differently performing device. Now, so the focus is how can we use these novel materials, relatively novel materials? Yeah, we're talking about materials that came out about 20 years ago for the organic and perovskites. Well, they were discovered a long time ago, but they started being used for solar cells about 10 years ago, effectively. So they're really recently revamped. So we're talking about how to fabricate printed, flexible devices using these materials and going towards a definitely more sustainable electronics and future. Again, you understand how easy it can be to deposit with an inkjet printer these active layers coupled to the deposition of metal electrodes and thin dielectric layers that all can be deposited by solution processes. Now, by solution with these materials, you can deposit thin films or single crystals. Of course, it takes a bit more of control of the temperature and the pressure, but still from solution, you can grow very, very nice single crystals. Today, I'm not going to discuss with you the single crystal. We will focus on the thin films that are what we need to achieve the target that I mentioned at the beginning. So a large area electronic detector. What is the advantages? Here you see them. And what are the problems related to their use as ionizing radiation detectors? The big negative part is they are really thin. And if I want to stop ionizing radiation, the volume makes a difference. Also, the atomic number Z, the average atomic number makes a difference. And here we're talking about organic material based on carbon, hydrogen, and oxygen. So how can they properly detect radiation? Because they don't really stop it. I will answer this question in a few slides, but here I want to stress the great advantage of the fact that they don't stop radiation, a lot of it. They have a huge radiation tolerance. They hardly stop it. So they can be used as detector for applications where you have high fluxes that would completely kill a silicon detector in few moments. The other great advantage is that they are human tissue equivalent. Being based on carbon, hydrogen, and oxygen, and being in a thin film form, they are very similar to a thin layer of human tissue. This is extremely important if you want to use them for medical application. And that means that you can use them directly onto the area that you are going to expose with the ionizing radiation without interfering with the beam that you're using and allowing it to be detected in real time while you're doing either the diagnostic or the treatment. This is an image showing the detectors that we are making and the idea that they can be really used while you're doing your medical diagnostic or your medical treatment. Briefly, let me focus on the applications that we are presently working on with these materials and with these devices. We're working towards medical application and the development of medical dosimeters, not imagers, okay? So to develop dosimeters that operate in real time with all these properties, we need to know what are the radiation that are needed and are of interest. So typically, you use X-rays for diagnostic, we all know it, but also for therapy. Typically, if you use them for therapy, you need to go to higher energy. And the very popular, unfortunately, tool is the gamma knife, which uses high energy gamma rays to target directly tumors and attack and kill them locally. So you use ionizing radiation for therapy when you want to directly attack and remove a localized tumor. Same story with protons. They're now becoming one of the more effective tools to remove cancer in a deep and controlled way. Of course, having protons is not as easy as having gamma rays or X-rays. You need an accelerator, and the cost of a proton therapy radiation center is an order of magnitude higher. We're talking about tens of millions of euros with respect to the cost of an X-ray therapy for cancer. But still, proton therapy is, again, really, really powerful. And why is it powerful? Because we all know that the different way of interaction between X-ray photons and protons and matter allows protons to deliver their energy exactly in the area and at the depth that you can design by controlling the penetration depth of the beam or by using multiple beams to reach a proper profile of deposition of energy into your target. So these are the two applications we've been working on. One is a large area 2D matrix that allows to monitor the area and the dose delivered when an X-ray, a radio X-ray treatment is done. And as you see, this is a real patient. The detector is a rendering for privacy purposes. And they can develop huge skin rashes, patients, because there is not a complete control of the area that is exposed and of the dose that is actually delivered. What I'm saying is that, of course, there is a control, but you can't do it in real time because if you put a silicon detector, it would absorb all the radiation, and then you would have to redo the measurement again. And also the silicon detector is not able to cover such a large area. So you won't be able to map the actual area that is irradiated and the dose that it has received. The other application is for proton cancer therapy. And this is endorectal balloon equipped with our sensors, plastic thin film sensors, that helps localize the proton irradiation delivered for prostate cancer, which is one of the major successful treatments that you can do with protons, but has the drawback of very often reaching the rectum, of course, unwantedly. So the idea of these detectors in the endorectal balloon are able to tell you if the irradiation is not going straight to the cancer, but is hitting healthy organs. These are the two examples, the one that I will talk to you today. But let's go back the applications, all right? So let's go back to the physics of how we can control the interaction between radiation and materials and use it to obtain these goals. When we want to fabricate a ionizing radiation detector, we have two ways. We can use direct or indirect detection methods. If we focus on the direct detection, that is probably the most straightforward. We use the incoming photon or proton as a beam able to directly generate electron hole pairs that are collected by the electrodes on the semiconductor. This is exactly what you do with silicon detector or cadmium zinc telluride detector, with the ones that we normally use. The other approach, indirect detection, is a two-step process that uses the incoming radiation hitting onto a scintillator. So the X-ray or the proton beams hit the scintillator and produce visible photons. So the energy is downgraded to visible photons, and these visible photons are sent to a photodiode that is then converting visible photons into electron hole pairs. Okay, so you need a photodiode and a phototransistor coupled to a scintillator. They both work very efficiently. There are examples in the literature with inorganic materials. And today I will show you what we do with organic and perovskite materials in this respect. This view graph, I think, is a sort of disclaimer that I want to show to start with, showing what are the current results published on organic in blue and perovskites in orange, direct ionizing radiation, and you see two things. First, that the curve is really rising in terms of performance, y-axis, over the years, x-axis. Secondly, I would like to stress the number of dots that you see, meaning that the research is really proceeding and spreading faster in this topic because it's really very promising. Third, the dotted line, red and black, that you see refer to the performance of commercially available, relatively large area, rigid inorganic detectors, polycrystalline cadmium zinc telluride and amorphous selenide. Look at the performance. So at a lab scale, we can already outperform these materials. Of course, there's a lot to do between the lab scale performance and the commercial performance of a device, but that is just to show we have really good hope that we can go somewhere with this research. Now, let's go to the point of how do these materials detect ionizing radiation. Here you see a very simple two-terminal device that is based on interdigitated gold electrodes deposited onto a PET, a plastic thin film. On top of it, we deposit by solution with an inkjet printer this molecule, which is called TIPS pentacene, that is one of the most popular organic molecules, like the silicon of organic semiconductors. This molecule structures itself spontaneously by drying, as you see in the right-hand side image, into long, thin crystalline needles. These crystalline needles can be micrometer long, and they are about 100 nanometer thick, so really, really thin, and they definitely remain flexible, okay? Now, what happens if you put them under an X-ray beam? Here you see the response as a function of time of the current measured in these two electrodes for an X-ray beam switching on and off. So you clearly see two things. First, that is very reproducible, stable, very low, very high signal-to-noise ratio, and that the delta I that you see is definitely not very high, but it's nanometer, and the volt that you need to apply is 0.2 volts. So this is a very good signal to be read by an electronic readout, so it's not a difficult signal to read. And what is very interesting is two things. First of all, the slow response. The slow response is basically telling us that there is a strong interaction between defects in the material. The slow response is related to the trapping and detrapping of defective states that have a long lifetime and that are known to exist in organic semiconductor. But let us also comment on the relatively intense delta I that we measure. We are getting a strong signal out of 100 nanometer thick organic material. How can this be? If we use, I would say, traditional physics or traditional models for interpreting the generation of electron hole pairs, that means that the X-ray beam generates electron hole pairs, they get collected. Let's do the calculation of what we should collect in our thin film. So the collected photocurrent is provided by the product of the elementary charge, the photon absorption rate, and the number of generated pairs. But how many photons can be absorbed? Let's try to estimate the absorbed photon flux. And we need to do this calculation to know what is the energy gap of pentasyn. It's about 2 electron volts, so very similar to inorganic semiconductor. The active area, the thickness, 100 nanometer, and the attenuation length. That gives us an absorption which is ridiculously slow. Look at that. The number of photogenerated carriers and therefore of the collected current should be less than 2 picoamps. So this model is not providing us an explanation of why we are measuring tens of nanoamps actually in practice. And honestly, it took us a few years to feel confident to believe that what we were looking at was not an artifact, because we were saying we're just measuring some systematic effect. There's an error in the measurement. We're not really collecting anything because we shouldn't be collecting anything. Now, that was until we realized that what was going on was the activation of a photoconductive gain effect, which is basically produced by the trapping of one of the two carriers, electron or holes, electrons in this case, that are generated by each impinging photon. So the impinging photon, X-ray photon arrives, creates an electron hole pair, not many, but those that are created are trapped at the defects that are present at the surface of my microcrystalline material. And therefore, the more electrical charges or electrons get trapped, the more my material needs to maintain charge neutrality, absorb or attract carriers from the injecting electrode. So to maintain charge neutrality, more and more carriers are sent through the electrodes. And that is a process that allows such materials to increase the collected current up to 10 to the 6th. This is happening because the charge trapped stay trapped for a very long time. So the lifetime of these electrically active defects is very long. And this is how we could actually also control this effect by modeling it. And we can model this photoconductive gain by seeing it as the ratio between two different phenomena. The first one is the transit time across the device. So the geometry of the device makes a difference. And the second one is the carrier lifetime. The carrier lifetime is severely controlled by the trapping states, energy and distribution. So if we introduce these parameters into this model, this analytical expression, we can very nicely model the response, in this case here shown for an increasing dose rate, of our very, very thin organic material, organic thin film, to X-rays. Now that we know what is the cause for this collected current, and we know that defects have a very strong role in capturing and holding on to one of the carriers, how can we exploit this knowledge to control the behavior of the material? This is the expression of the photocurrent gain, G, that if we introduce the expression of the tau R and the tau T, we can see here in full bloom, and we clearly see what are the parameters that we can play with to enhance G and thus the collected photocurrent. The first thing we can work on is the morphology and the interface, the morphology of this polycrystalline film and the interfaces, because that's where the defects, the electron traps are located. Then we can play with the mobility, you see, direct proportionality. The higher the mobility, the better the gain. Then we can play with the collected carrier, collected current, by increasing, if possible, the atomic number of my material. But how can I do it? Thanks to the very easy tailoring of our organic thin films, by simply, chemists took a while to do it, by changing silicon instead of germanium, for example, in the molecule we're using. This difference, which is not minor, already increases the absorption of 2 or 3 times, or at least 3 to 4 times. And finally, we can change the device architecture, and using a transistor, of course, is much better. Here I showed you the results on a very simple 2-terminal device because we are focusing on the material, not on the device. But once you know how the material works, you use a transistor, so you can use its intrinsic amplification to further exploit the gain. Now, I would like just to focus today on the role of morphology and interfaces related to the mobility, so really on the material property at a physical level. Now, here I'm showing you another molecule that we are using, TMPS, and we used it blended with polystyrene. You make blend very nicely, easily in your lab, in a becker. You blend them, and then you deposit them using a steel bar, like a little brush. You use them to coat what? A substrate that contains a silicon gate, a dielectric, and metal electrode. So it's a bottom gate transistor that you fabricate here by depositing this organic semiconductor layer. This is what you obtain in terms of polycrystalline film. You can see the optical image. In the optical image, I'm showing you the difference between a pure TMTS film and a blended film. Why am I doing this? Because we noticed that this blend is not really homogeneously distributed throughout the film, even if the film is really thin, few hundred nanometers, but polystyrene tends to segregate at the interface with the bottom. And this is not a negative thing because it helps passivating all the interface trap states that are located at the bottom interface. Thanks to this passivation that you achieve simply by doing the blend together, you clearly see that the mobility of the blended polymer is much higher. And it is much higher because you're passivating the traps that are negatively affecting the transport for majority carriers. And that is why we get a much higher sensitivity, so a much higher gain for ionizing radiation X-ray detectors, okay? So we can learn how to passivate majority carrier traps that are killing the mobility in our material and leaving the mobility high. The other traps that we have to control are the traps around our crystals, our polycrystals. Why? Because that's where the electron trapping, so the minority carriers get trapped. And these are the traps that are more directly related to the gain. And as we'll see in a moment, these traps are beneficial and we actually want to keep them. Let's see what happens if we change the grain size, which is something that, thanks to this material, we can do very easily because we can simply change the speed of deposition. So if we change the speed of deposition for this bar, look at how different is the dimension of the grains that we obtain, low speed and high speed. Still the same story. We go with the nozzle printer directly onto a transistor bottom gate structure. So what we get is that if we go at low speed, we have big, well, relatively big grain size, about 17 micrometers square. If we go to high speed, we go down to grains that are 1/3 smaller. What is interesting is that the mobility does not change much. Look at the low and high speed, same mobility, but the sensitivity increases 4 times. So something is really telling us that the grain size makes a difference. And please note that the higher sensitivity is achieved for smaller grains. Smaller grains means greater surface area and larger number of electrically active traps that can interact with your incoming charge-generated pairs. So putting it together, this is another material, TIPS, pentacene, blended with polystyrene. And we could definitely see that if we change the polystyrene and TIPS ratio, we can control the mobility and the mobility measured by this transistor, which has a maximum for certain TIPS polystyrene ratio, and that is exactly going in the opposite direction of the density of interface majority carrier traps. And that is, again, telling us that the sensitivity is sensitivity to X-ray is proportional to the mobility. So by putting these things together, we can say that interface all traps are good have to be removed to keep the mobility high, while by controlling samples with the same mobility and different grain size, we see that the gain is much higher for smaller grain size that allow us to increase the surface area affected or generating electron traps that are definitely beneficial. Now, let me show you similar films based on perovskites. Look at the perovskite very rough aspect. These are SEM images of MAPI, so methyl ammonium lead iodide perovskite. This is a pure MAPI thin film. The second image is MAPI blended with another polymer, PCBM, because we really understood that these blends are useful in passivating selectively the traps that we don't want. And here is what a very simple 2-terminal device looks like. Here it is. Here you see like 4 or 5 pixels that are here. What is interesting with perovskite is that they have a higher atomic number, and you can deposit them up to 10 micrometer thick. So with perovskite, we exploit not the human tissue equivalent, but we exploit the fact that we can still keep a flexible plastic device, but with a much higher absorption cross-section for radiation. So we can stop higher energy photons. And this is the response to X-ray. You clearly see this is the X-ray beam on and off for different bias applied in positive bias and negative bias. You see the nice reproducibility for each bias, and of course the different, greater or increasing delta I in collected current produced by different increasing bias. What is nice to see here is that the response of MAPI, pure MAPI, and MAPI with the blend is very different. The red signal, the red curve are related to the blended material, meaning that the one with the blend has a much better performance. Why is it so? We went to the synchrotron in Grenoble to try and explore what is happening at a local interface of these grains. And we did a simultaneous X-ray fluorescence and X-ray beam induced current analysis, XBIC. So basically we used the very thin nanometer 50 nanometer beam of X-ray to stimulate both X-ray emission, so X-ray fluorescence, and collected and current that we could collect thanks to the fact that these materials are conductive. So the idea is that here you can see how the two maps provide different information, the XRF and the XPIC maps, but the message is that thanks to this technique, you clearly see that the boundaries of these crystals provide different information. In particular, you clearly see that when you have pure MAPI, the signal at the boundaries is much higher for the collected current. When you have the blend, everything is smoother. Why is this happening? It is happening, again, because there is a different electrical activity in blended material where the polymer passivates the polycrystalline, the polycrystals, and in the elements where there is no polymer. This is basically what we achieve. So the message is, if there is the polymer, it can passivate nicely all the grains, allowing for a much better transport through the grains and from one grain to the other of the electrical carriers created. So again, to conclude, we realized that both in perovskite and organic thin films, the physics of the electrical defects and their interaction with the incoming radiation was really important. Just to go quickly to another way of exploiting thin films is going to 3D versus 2D perovskites. If you change the dimensionality of your film and don't go for 3D perovskites, but go for 2D perovskites, you can take advantage of some of the features of 2D materials that can be nicely exploited. 2D perovskites have a lower mobility, but have a much lower ion migration. And ion migration is one of the killing effects that is presently blocking perovskite from being widely exploited, even in solar cells application. Ion migration is what happens when you apply even a small bias to a perovskite film, and typically you start seeing these ions moving, and eventually the structure gets disrupted and the film stops maintaining its property. So 2D materials, 2D perovskites are much more stable, even if they have a lower mobility. So basically, we started checking how their behavior as radiation detector was. And here is, again, a solution deposited film, polycrystalline, thickness of about 2 microns, but we were happy to use it because it has a very, very low dark current. It means the transport only can happen since it is a 2D material, has a very high directionality. And this reduces the dark current, so the current that you collect, without doing anything to your material. And the result is that you have a very, very good detector because you're starting from a material that is basically showing a almost zero current. And whatever you induce with your injected carriers is a huge signal, because you always measure the delta I over the I. If the I, the dark current, is very low, any delta I produces a fantastic signal to noise ratio. And here you see how nice this on-off switching signal and how stable it can stay. It is very stable under the typical irradiations that we use for mammography, and it has been stable also after 18 days of storage in air without encapsulation. Again, here you see this continuous on-off switching that it's important to assess if you really want to think about applying this material. So 2D perovskites are much more stable, provide a fantastic response, and thanks to their layered and directional transport and lack of ion migration, provide very, very good performance. Here is an example of a device that we have developed. This is the active sensor. You see an 8-pixel matrix that we connected to a readout, portable readout, because again, you need so little power supply and so little readout. And this device was used to monitor gamma emission from a patient that had been going radiopharmaceutical injection to kill cancer cell. So as you know, these patients remain very often radioactive. So they have to stay and wait until the radioactive effects cool down. And these sensors were very good in detecting and monitoring the decay of the gamma emission from the pharmaceutical that was in the veins of the patient. Just to show you a very quick thing, we also can deposit perovskite on textile if you really want to go for wearable devices. This was just another way of showing how versatile these materials are. But let me just go quickly to the final slides that I want to show you that are related to indirect detection methods. So far I only talked to you about thin films based on organic and perovskite for direct detection. But we can have flexible, fully organic, indirect detectors by putting together an organic scintillator and an organic photodiode or phototransistor. Here is the structure you want to put together, basically. And why do you do it? Because it's very good if you want to detect protons. So proton detection works very nicely if you have a scintillator that is able to collect the protons and emit visible radiation, then collected by your organic photodiode, in our case was a phototransistor. Everything needs to be put together, but what is really nice if we want to explode the structure, remember that we will need an organic-based scintillator able to convert protons into visible photons. And then we have a transistor here, organic phototransistor. This is the organic active layer we are using. It's a different molecule called DNTT. Why do we change the molecule? Because we need a material that is absorbing exactly the wavelength emitted by our scintillators under proton irradiation. So you need to have a good optical match. That is what you see here. In purple, you see the absorption curve of the entity, the active layer of the organic device, organic photodiode, and in blue and red, the emission wavelength of the scintillator. You see very nice optical coupling. So you couple them together, and what you see, this is the scintillator, the plastic thicker layer, and this is the phototransistor. You see, you really put them together and obtain a very nicely bendable device, which is much more bendable than what you would obtain with scintillators that are still plastic, but not specifically developed to be flexible. Okay, so there's quite a lot of work that has to be done. Again, what happens under protons? This is the response to our device to 5 MeV protons. This is the response under yellow, in the yellow rectangle under proton exposure, and the rest is the decay after the proton beam has been switched off. What is interesting is that the response scales nicely with the proton flux, so it is a dosimeter. And what is really nice is that the transfer characteristic of the organic phototransistor before black and after red, multiple ion protons or irradiation are not affected. So indeed, the scintillator absorbs all the protons and no damage is produced in the organic phototransistor that can be nicely bent to various radiuses. Now, what is interesting to conclude is that understanding what is going on and what is the final readout that we get is not always trivial. You always have to go back to the physics. Why? Because that is what you get under increasing proton fluences. This is the current And this is the time. What you see is that indeed, by increasing the proton fluence, the signal increases, scales linearly, but also there is what could seem like a baseline shift. And you would think, okay, there is a baseline shift, something is happening, a degradation of my material, whatever. But we see exactly the same response of the full device under protons here, and of the phototransistor alone under photons. So it is not related to a damage induced by the protons, but it is intrinsic to the response of this organic semiconductor, which is controlled by trapping states, where trapping states have a strong role. In fact, we developed a simple kinetic model, simply taking into account the presence of two differently distributed trap states that have different trapping times. One is fast and one is slower. And if we model the presence of these two narrow distribution or two distribution of defects, we can really see, this is the basic model, that under irradiation, we create the defect or we activate the defect. That is something we still do not know. We're still trying to understand if the radiation creates the defects and then everything happens, or activates it. And that is what happens. So you either create or activate the defect, and then you have all the recovery that can of the defects that can be induced by the photons or simple thermal recovery. The final message is that by using these two distribution of traps, we can model very nicely the response. The response is the red dotted line. So keep your eyes on the red dotted line that provide a sort of baseline increase. And then we have these two components, the swift fast component, which is the green one associated to this trapping state, and the blue persistent component associated to the slow component. And if we put these two in the model that I showed you before, we can nicely reproduce in black and model the response of the device. So the message is we get exactly the same response, photons onto the phototransistor and protons and the full device. So definitely this is due to the organic phototransistor, and there is no damage of the phototransistor. And the message would be, so why not using, instead of an organic phototransistor, another type of semiconductor that allows you to have a faster response and avoid this kind of slow component that stays? Well, the answer is yes, if you find a material that can be deposited by printing over large area and maintain flexibility, okay? So you can't have everything always at once. But what is really nice is that by understanding the origin of this curve, we can definitely control and use it as a quantitative tool, calibrated tool, to measure the dose of protons actually received onto the device. This is the final test that we just finished doing. We used a dummy. This is a torso of typically used for simulation that we tested at TIFPA in Trento, where they do irradiation with the 200 MeVs, and we positioned our endorectal balloon exactly where it was meant to be in a proper cancer treatment, and we could assess that we could see when the beam was hitting the balloon and when the beam was not hitting the balloon, and that the response was proportional and linear to the dose received. So, to conclude, my message today would be that there is a lot of work that we can do on the physics of materials if we want to exploit even these novel materials that seem to be a bit, original and strange to handle, because novel materials have a great potential that is still mostly unexplored if we want to use them fully, and that a lot of work is still needed in terms of transport properties, defective states, interfaces, and surfaces, because by playing with them and knowing what's going on, and you need a physics study to understand that, then you can do very interesting application. So that is just an acknowledgement of all the various projects that has funded this research, which is always very expensive. And this is the research group that has been working a lot on this in the past years. So thanks to them, and thank to you for your attention.